In this tutorial, we are supposed to learn how to optimize the slope angle. And question is, what is the slope angle optimization? In open pit design, slopes are made as steep as possible to reduce cost, provided that a suitable safety factor is maintained. We aim to determine the optimal slope angle for an open pit excavated in weak rock according to the mining company's specifications. The safety factor for the critical slip surface must be greater than 1.25. Okay, I open the initial model. The first step, I go properties, define material. The slope material are composed of a sediment layer and a weak weathered rock overlaying the bedrock. Let's before to determine the safety factor, measure the overall slope. Go to the tool, dimension angle, click on the crest of the slope, and then go on the toe of the slope to create a line connecting this point. Next, drag the mouse horizontally to the right, draw the overall slope angle. Okay, in the initial design, overall slope angle is 41, and we will attempt to optimize this angle. Compute this model. Interpret. Okay, the safety factor is approximately 1, which is lower than 1.25 required by the mine. A value of 1 suggests that the slope is close to the failure and therefore poorly designed. We will reduce the slope angle by different degrees and observe the corresponding change in the safety factor. Okay, I close and go back to modeler. We will generate 4 different scenarios of the initial model, each with a different overall slope angle. In each successive scenario, the slope angle will be reduced by 4 degrees, and a stability analysis will be carried out for each case. Okay, select boundary, a slope angle wizard to active prompt line. Okay, click on the initial vertex at the toe of the slope, then move the cursor upward along the slope face until you reach the vertex at the crest. Click on the crest vertex to open a slope angle wizard dialog. As an alternative, you may input the coordinates of the toe and crest here. Okay, leave the default option project horizontally selected to modify the slope in horizontal direction, and then choose the clockwise. In this case, it will produce flatter overall slope angle. Okay, enter 4 in both field for generating groups and defining the increment angle. This creates 4 scenarios with the overall slope angle reduced by 4 degrees in each step. Please note that the checkbox labeled project only the crest of the slope and move each vertex relative to it. This ensures that the toe remains fixed while only the crest is adjusted. Okay. 4 new groups have been generated in document viewer. click on group 2, slope angle 4 degree. Okay. Okay. The overall slope angle here is 37 degree. Okay, and group 3. The slope angle here is 33. Group 4 slope angle 12 degree. The slope angle is 29. And group 4 slope angle is 25. Okay, in general it's better to begin with the maximum slope angle and then reduce it using the change slope angle option. In this approach, Slide 2 will reliably trim the new slope face to match the existing material boundary. However, if you begin with a shallow slope and increase the angle, Slide 2 will need to extend the material boundary that intersect the slope face into regions where no data is available. As a result, the software output may not match your expectation, and you may need to manually adjust the new geometry to reach the correct boundaries. Okay, we run the model. This 4 group. Okay. Interpret. Select this, just this 4 group. Okay. Click on tile window here. View legend option decimal. Okay. The critical slip surface and their corresponding safety factor for both Bishop simplified are displayed for the groups as illustrated in the image. Now we create a plot of this data. Select data and graph graph scenario plot. Okay, sampler, show sampler. Okay, from the Bishop result it suggests that the optimum factor of safety of 1.25 can be achieved at an overall slope angle between slope angle 12, okay, here, and 8 degree corresponding to 33 and 29.